Established Program 2015 through 2000 ways to use mobile learning to create, to communicate, and to learn in new and different ways. We hope that you will enjoy today's Periscope Spotlight and try to use at least one of the tools or practices in your own classrooms. Thanks.
All right, so let's walk in and we'll see what's going on. We're going into an organic chemistry class with Dr. Matthew Smith in the natural science building here at Walter State. He's going to be using the iPad Pro, and we can see what's going on in the classroom today.
So, Vidig has the superpower to turn a carbonyl and a carbon nucleophile into an alkene. And so, we will start just by looking at the general basics of the reaction. It starts with a compound that we haven't seen before called triphenylphosphine. And if we put our nomenclature skills to use, we can see that triphenylphosphine is right there. And so triphenylphosphine has a lone pair of electrons on the phosphorus, and it reacts through an SN2 mechanism with primary and secondary alkyl halides. And as it does, it attacks the carbon center, kicks out the leaving group, and the salt has the positive charge localized on the phosphorus, and the anion that was kicked out in the SN2 is bearing the negative charge. Now, the whole purpose of the Vidig reaction is to form a carbon nucleophile, and every carbon nucleophile that we have seen so far has a negative charge on the carbon. So once we form this salt, this hydrogen right there that is located next to the positive charge on the phosphorus feels a little bit lacking in electrons. Right? So it's fairly electron deficient. It's fairly acidic. And so a strong base something like butyl lithium can come in and remove that proton, and when it does so, it puts a negative charge on the carbon. And so this forms a special type of carbon nucleophile called an ylide, Y-L-I-D-E. Now, in terms of reactivity, this ylide is going to behave exactly the same as we saw for the Grignard and for the organolithiums, all of the other carbon nucleophiles that we have seen. The mechanism for how this carbon nucleophile reacts with carbonyl compounds is here. I pulled it from your text, right? But instead of actually just talking through this, let's work through an example. And we'll go through the mechanism in the example. So here's some problems, and it wants us to take these primary and secondary alkyl halides, convert them into the phosphonium salts, convert them into the ylide, and then react them through the Vidig reaction to form the alkene product. Okay. So if we take the first reagent, so if we take 2-bromopropane, the first step that we saw was the SN2 reaction. So
Oh, while you're doing that,
did you ever update software and the update doesn't work the way that
Dr. Smith,
Yes.
I want to ask what you're mirroring with.
I'm using the Apple TV. All right, so we'll just wing it. I'd hoped that we would be able to, that's what they say, go back and all the tests. Come see me next time before you come in to wing it So the triphenylphosphine comes in and attacks the carbon bearing the leaving group, kicks out the bromine. And so we're essentially forming a bond between the phosphorus and the carbon. If multitasking would work, we would be able to see this, right? That leaves a positive charge on the phosphorus and a negative charge there on the bromine. So we'll add in our charges. So step one, attack of the triphenylphosphine. Sounds like a bad sci-fi movie.
Sounds like a great sci-fi.
Step two, we're going to remove a proton using our strong base. So we continue our reaction across. N-butyl lithium. Now, if we look at our salt, there are 2 hydrogens available.
Dr. Smith?
Yes.
Do you have to use n-butyl lithium, or can you use any sort of base?
You need a strong base, right? So the reason we use n-butyl lithium is because it's such a strong base.
Okay, but any strong base?
Hydroxide's not going to work. Probably p-butoxide's not going to work very well. You really want something with a really large pKa and conjugate acid. You could probably get away with something like LDA that we saw back in Organic 1.
Okay.
All right, so which hydrogen do we want to remove? The red one or the blue one? The blue one? Does that fit what we saw in the last step? No.
It has to be the one.
It has to be the one adjacent to the, or the one that is on the carbon that is now connected to the phosphorus. And so we can see that this really implies the statement there that this will not work for tertiary alkyl halides. At that point, you have no hydrogen to remove in the second step. All right, so our base is going to remove the red hydrogen. I'll put the negative charge there on the carbon. Negative on the carbon, positive on the phosphorus. And so here is our billet.
Good morning.
This is our carbon nucleophile. Now I told you that the mechanism for the next step is in your notes, and it's in your text, but I really want to draw it out. And so the way that we draw this out, it's easiest to think of these molecules coming together on top of each other. Right? So it tells us that we're going to react each of these with acetone. And so draw acetone kind of sideways. We're going to have some really skewed bond angles whenever we do this product, but this really lines it up well for us to see where the atoms and the electrons are going. And then underneath acetone, draw your illet. And do so that the phosphorus and the oxygen line up. And so that the carbon in your carbonyl lines up with the carbon in the illet. more space in it. Now, in the last reactions that we saw, the nucleophile always attacks where? The carbon, all right? So the nucleophile that we just formed is going to attack the carbon in the carbonyl. Right? What happens to the pi electrons between the carbon-oxygen double bond? They go outside, right? Usually they go up onto the oxygen. Now, though, since these are lined up very well, they have a better place to go. They can go there onto the phosphorus. So,
Have we ever
Pardon?
done that before?
we have not yet, just because our other nucleophiles didn't have that positive part actually built into the
So as you
molecule.
can
It was
see,
easier just to put the
The
electrons on
iPad
the
Pro has
oxygen.
many advantages
come around
facing
the
inside the
protein.
classroom, and it's being used effectively this morning in this organic chemistry class. So
So
we're glad
our
you joined
two
another one of
red
our
arrows
20-minute
show that we have formed the
mentors
bond
here,
between the two
series
carbons
on Tuesday
and between
mornings.
the oxygen
Look forward to
and the
seeing you
phosphorus.
next week.
So
Let
let's
us know if
draw
you have
that
any
out.
questions or if we can help you at all.
See what we get.